Hi, I'm Rose, and I'm going to talk about inverse kinematics proton scattering and analysis of Titanium-54 and 56. Inverse kinematics proton scattering is like throwing a baseball bat at a baseball. What we're doing is we're throwing nuclei at protons, and those protons cause the nuclei to become excited and thus they emit gamma rays. This whole experiment was done at the National Superconducting Cyclotron Lab, which is part of Michigan State University. We don't have the equipment and our scientists to do it, so they just give us the data. But this experiment started by the fragmentation of a stable germanium beam in a beryllium target. That created the cocktail beam of nuclei that we worked with in this experiment. The cocktail beam nuclei first goes through the A1900 fragment separator. The A stands for analysis, and the 1900 is just the strength of the magnet. And this fragment separator is aided by an aluminum wedge, and together they separate the fragments by atomic number, and that's just the number of protons that each nuclei has. Then the beam of nuclei goes down to the S800 magnetic spectrograph. The S800 magnetic spectrograph is essentially a magnetic prism that detects charged particles by energy difference. So before the beam goes through the Ursinus College liquid hydrogen target with Gratina around it, the particles in the beam are identified by energy loss, which provides charge separation, and by time of flight from the A1900 focal plane to the object scintillator, which is that green box up there, and that provides mass separation for us. Then the beam goes through the Ursinus College liquid hydrogen target, and again, the particles are identified by time of flight and by energy loss. This is Gratina with the Ursinus College liquid hydrogen target. Gratina stands for Gamma Ray Energy Tracking Array. So this basically just tells us what gamma rays are emitted by the nuclei. But what Gratina also does is it Doppler reconstructs the gamma ray spectrum for us. The reason we need to do this is because the Doppler effect also affects light. How Gratina does this is it can determine at which angle the beam is hitting the target, and by doing that it can calculate the beta value, which is just the fraction of the speed of light the beam is traveling, and it can use that to Doppler reconstruct the spectrum. We calculated that Titanium-54 was traveling at 41% the speed of light, but Titanium-56 was traveling a little bit slower at 40% the speed of light. This is the incoming cocktail beam particle identification. Notice time of flight, which is mass separation, is the x-axis, and energy loss, which is charge separation, is the y-axis. Also notice Titanium-54, it's a much neater blob there. You can see it's just, the blob just outlined. But Titanium-56, there's not really like a blob there, it's kind of just, the green and the blue. So our data for Titanium-54 is going to be better because we're sure that we got Titanium-54 in that circle, but Titanium-56 could have gotten Titanium-55 or something else in it. And there's less counts there too, so just because of that, our data won't be as well either. The data won't be as good either. This is the gamma ray spectrum for Titanium-54. The first peak you'll see is what we call an unresolved doublet. We actually measured it at an energy of about 1,015 keV, but we're calling it an unresolved doublet because there's a database that gives us the known energy values for gamma rays from proton scattering and other experiments in Titanium-54, and there's known gamma ray at 1,001 keV and one at 1,021 keV. We weren't actually able to tell which gamma ray we had in this one, so we put them both in the fit, and it fits pretty well, so we included both. Second gamma ray you'll see is 1267 keV, and this is exciting because it hasn't been measured before in proton scattering or even Coulomb excitation or any experiment in Titanium-54, so we're the first ones who measured it, but because of that, we can't say much about it. And the last peak you'll see, 1505 keV, that's the first excited state energy. It's the 2 plus to the 0 ground state. I'm going to talk about that later, why that's important. The dark gray you see is the room background, and that accounts for anything else in the room at the National Superconducting Cyclotron Lab that could have contaminated the gamma ray spectrum. The lighter gray you see is the prompt background. We don't really know much about it. We can't say anything about it really, but we know it's there, so we included it. And there's people at NSCL who are currently working to try to figure out more about it. This is the level scheme for Titanium-54. There's two of them because, like I said before, 1267, we don't know much about it. We don't know if it's a feeder into the 2+ state like the other gamma rays, or if it's not a feeder. So because of that, we made two level schemes. Here you see I listed it 3- state, but we don't know if that's right either. It could either be the 3- state, the 2+ state, or the 4+ state. We do know for a fact that it's not at the 6+ state because you can't get that much energy just from proton scattering. Notice that some of the lines are thicker than others. I scaled the thickness by intensity of the gamma ray. So you'll see the 1495, that's the thickest because that's the 2+ to the 0 ground state transition, so that's 100% intense. And then you'll see like the 1001 is much thinner, so that's like the least intense gamma ray in there. Here's our gamma ray spectrum for Titanium-56. There's another unresolved doublet there. We have a 2+ to the ground state, which is 1128, and we also have the 4+ to the 2+, 1160. When I calculated intensity, I only got about 10% intensity for the 1160 keV gamma ray, so not much is there, but some's still there, and it makes it fit better to include both of them. Here we only have the prompt background because, unfortunately, the background had more counts in it than Titanium-56 did, so the background section would kind of just cover up this whole spectrum, so we didn't include it. But notice that this is much less pretty than the Titanium-54, which I was talking about before, because we don't have as many counts in the spectrum. This is the level scheme for Titanium-56. I didn't scale the thickness of the lines by intensity because the 1160 was only intensity of 10%, so that wouldn't be very big. You can just see it's 4+ to the 2+. It definitely feeds, and this is pretty simple level scheme. This gets into why I even did this research. The short reason is to better understand nuclear structure, but by that we mean we want to look at the possible shell closures at n equals 32 and n equals 34. And to do this, we looked at the first excited state energy, and we also calculated reaction cross-sections, which in turn we use that to calculate the deformation lengths. But first, we'll look at the first 2+ state energies. We have, for n equals 28, we know there's a closure there at that shell. People have been proving that before. As you'll see, the energy, the first 2+ state energy there, for most of those nuclei, they're around 1500, but you'll see silicon is a lot lower, and that's really the only data point that doesn't fit on this graph, but you can ask me about that at the end if you'd like. And you see to the right of that, n equals 32, the open triangle for titanium, you'll see there that the first excited state energy is about 1500 as well, so that's comparable to the n equals 28. So that can give us evidence that there would be a shell closure at the n equals 32 level. But if you look at n equals 34, at the open triangle there, that's about 1100 keV, which is about 400 keV lower than the first excited state energy in n equals 32 and n equals 28. So we have evidence there. We think we have enough evidence to conclude that there is not a shell closure at n equals 34. But we also look at the deformation lengths. The open circles have been measured by people before me, but the closed circles I actually measured, because n equals 32 is Titanium-54, and n equals 34 would be Titanium-56. But you'll see here the deformation lengths, it's kind of opposite the energy. We want the deformation lengths to be lower for there to be a closed shell. You see at n equals 28 and n equals 32, these are pretty small deformation lengths, about 0.8 FM, where you see n equals 24 and n equals 34, they're like 1.0 or more FM, which means that the amplitude of the vibration is higher, or the just the deformation in general is higher, which would lead us to believe that there is not a shell closure at either of those. So that concludes our research.